Hello everyone. In today's lecture, we will see some miscellaneous questions based on relations and functions, right? So, miscellaneous exercise part 1. Let us start with the miscellaneous exercise part 1. The images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So let us start with the first question, which says, show that the function, we are given a function f from real to x belongs to real, x is from -1 to 1, right? Got it? And the function is defined by fx is equal to x upon 1 plus mod x, right? X upon 1 plus absolute value of x, right? And x belongs to real is 1 1 and on 2, right? So the we have to basically show that the given function is 1 1 and on 2, right? That is, the given function should be the bijective, right? So what are the conditions of functions to be bijective, right? We all know that for a bijection, function must be both 1 1 and on 2, right? Got it? So first we have to check 1 1, right? So how will we approach, right? For 1 1, we can say that for x1 and x2, if suppose f of x1 is equal to f of x2, right? Got it? For the function, if f of x1 is equal to f of x2, then when we will solve this function as f of x1 is equal to f of x2, then after solving this, we should get x1 is equal to x2 only, right? X1 is equal to x2 only, right? This is analytical approach. Got it? This is analytical approach. So we will go with the analytical approach in this question. One is graphical approach also. What the graphical approach says? Graphical approach says that if we draw the graph of the function, right? If we draw the graph of the function, and if we draw any line which is parallel to the x-axis, right? Then that line must cut the graph on exactly one point, right? The line parallel to x-axis must cut the graph at the one point. Then only the function will be 1 1, right? So we will not go with the graphical approach in this, right? Because the to draw the graph of x upon 1 plus mod x is not easy to draw, right? But like if we have a certain function whose graph is easy to draw, right? We might go with the graphical approach, right? Because if we can easily draw the graph, we can easily say that the function is 1 1, right? But for the function, if the graph is not easy to draw, we will go with the analytical approach, right? So for the analytical approach, we will say if f of x1 is equal to f of x2, then it must be x1 is equal to x2 only after solving f of x1 is equal to f of x2. This condition is for the 1 1, right? 1 1. Got it? For onto, what should be the condition? For onto, the condition should be that the codomain should be equal to range of the function, right? The codomain. See, this is the codomain. Got it? This is the domain and this is the codomain, right? So the codomain should be equal to the range of the function, right? So we will also check whether the given codomain is equal to range of the function or not, right? Got it? Okay, so let us move to the solution of this question. You have 10 seconds to think about this question. After that, we will discuss the solution, right? Okay, let us move to the solution part. So we are given a function f, which we have discussed already, as f r2 x belongs to r, x is from -1 to 1, defined by fx is equal to x upon 1 plus absolute value of x when x belongs to real, right? We basically have to show that the given function is 1 1 and on 2, right? So it is given that the function f is from real to x belongs to real, x is from -1 to 1, right? And it is defined as fx is equal to x upon 1 plus absolute value of x, right? And x is x belongs to real. Got it? Suppose, so what we have to do basically, we have to take fx is equal to fy, right? We might take fx1 is equal to fx2 also, right? This is just a variable x or y, right? Or x1 or x2. Got it? So we can take fx is equal to f. If fx is equal to fy, then we basically have to prove by the analytical method that x should be is equal to y. Then only the function will be 1 1, right? Okay, so now it can be observed that if x is positive and y is negative, suppose x is positive and y is negative, right? We will take different conditions, right? Like whether x is positive, y is negative, when x is negative, y is positive, when both is negative, and when both is positive, right? Got it? So we will check whether by taking different conditions is fx is equal to fy is coming in the domain or not, right? So it can be observed that if x is positive and y is negative, right? Suppose we know the like property of absolute value function, right? Suppose we have absolute value function, how it varies. It is equal to x when x is greater than 0, right? And it can be written as negative x when x is less than 0, right? So it can be written as x upon 1 plus x, and it will be equal to c when y is negative. X is positive, so we can write it as plus x, and y is negative, so we will write it as negative y, right? So x upon 1 plus x will be equal to y upon 1 minus y, right? When you will solve this, you will get 2xy is equal to x minus y, right? Now since x is positive and y is negative, right? So x is positive, y is negative, therefore x is greater than y, right? X is greater than y, therefore x minus y should be greater than 0. Got it? X minus y should be greater than 0. But since x is positive and y is negative, therefore 2xy is negative, right? So we are given a equality in equality in which 2xy is equal to x minus y. X minus y is always positive, but 2xy is always negative. Can it be true? No, right? So a negative function cannot be equal to positive function. Therefore, then we know that 2xy will not be equal to x minus y, right? 2xy will not be equal to x minus y. Thus, the case of x being positive and y being negative can be ruled out. Got it? Now, under a similar argument, x being negative and y being positive can also be ruled out. Got it? By using similar argument. Now, therefore, x and y have to be either positive or negative, right? Both x and y have to be either negative or positive. It cannot be possible that either x or y, uh, 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 one of the x or y should be either positive or negative, right? Both should have to be either positive or negative, right? So let us take this argument, right, and check whether we are saying right or not, right? If this argument again fails, then we can say that like our all the arguments are failed, so function is not 1 1, and function will not be defined either, right? So when x and y both are positive, therefore let's take fx is equal to fy, right? So both are positive, then we can write it as x upon 1 plus x, right? And y upon 1 plus y, right? Because both x and y are positive, so we will write x as plus x and y as plus y. When we will solve this, we will get x plus y, x plus xy is equal to y plus xy. Xy and xy will be cancelled out, and we will get x is equal to y, right? So if we have assumed that fx is equal to fy, then it is coming out to be x is equal to y, right? So now let us take another case when x and y both are negative, right? So we have checked that when x and y both are positive, we got that the function is coming out to be 1 1. Now for the condition when x and y both are negative, we have if fx is equal to fy, then we can write x upon x1 minus x and y is equal to y upon 1 minus y. When we will cross multiply and solve this, we will get x minus xy will be equal to y minus xy. So it will be cancelled out, xy and yx will be cancelled out, and we are getting x is equal to y. Got it? So for both the conditions, we are getting x is equal to y when we assume fx is equal to fy, right? Therefore, we can say that the function is 1, 1, right? So for the bijectivity, f should be both 1, 1 and 1, 2, and we have proved that f is 1, 1. Now we will see whether f is onto or not, right? Now let us let y belongs to real such that, like, we will see whether codomain is equal to range or not, right? So let us assume first codomain is equal to range, right? So for y belongs to real such that y is from -1 to 1. If y is negative, then there exists x, which is x is equal to y upon 1 plus y. Why? When y is negative, see y is negative, then y is basically x upon 1 plus mod x, right? See, denominator term is basically positive always, right? Because 1 plus mod x. Since y is negative, there it should be negative x, right? X can be written as negative, x is negative, right? So when x is negative, x absolute value of x is basically x when x is greater than 0 and negative x when x is less than 0. Got it? So if x is negative, then it can be written as y is equal to x upon 1 minus x, right? And when we will solve this, y by cross multiplication, y minus xy is equal to x, right? So y is equal to x times 1 plus y. So what we will get? We will get x is equal to y upon 1 plus y, right? Which we have which we got here, x is equal to y upon 1 plus y, right? Clear? So if y is negative, then there exists x such that y is equal to x such that there exists x is equal to y upon 1 plus y by using this, right? So let us take fx is equal to let us take fx is equal to f of x is y upon 1 plus y. So fx can be written as f of y upon 1 plus y, which is equal to y upon 1 plus y upon 1 plus y upon 1 plus y, right? So we can write it as y upon 1 plus y upon 1 plus minus y upon 1 plus y, right? Minus y upon 1 plus y. Got it? And after solving this, we will get y upon 1 plus y minus y. So it will be cancelled out and we will get f of x is equal to y. Now let us check for fy, right? If y is positive, this condition fx is equal to y is for the case when y is negative. Now let us take if y is positive, then there exists x which will be equal to y upon 1 minus y by the similar way, right? By the similar way, how? When y is equal to given as x upon 1 plus mod x. See, when y is positive, then x must be positive. So it can be written as y is equal to x upon 1 plus x, since x is positive. So it will be equal to y plus yx is equal to x, right? So x can be written as y upon 1 minus y, right? After solving this, you will get. So if y is positive, then there exists x which is equal to y upon 1 minus y belongs to real, right? Such that fx is equal to f of y upon 1 minus y, which is equal to y upon 1 minus y upon 1 plus mod y upon 1 minus y, right? And it is equal to y upon 1 minus y upon 1 plus y upon 1 minus y, which after solving you will get y upon 1 minus y plus y. It will cancel out. So we will get fx is equal to y, right? We will get fx is equal to y. Got it? So for both the cases, fx is coming out to be equal to y. That is codomain is equal to range, right? Codomain is coming out to be range. Therefore, f is onto. Hence, the function is 1, 1 and onto both, right? So we have proved that the function is both 1, 1 and onto. Clear? Okay, let us move to the next question. Next question says that show that the function f from R to R given by fx is equal to x cube is injective. What is injective means? Injective means 1 1. We basically have to prove that the function fx is equal to x cube is basically 1 1, right? From this relation R to R, right? We basically have to prove that fx is equal to x cube is 1 1 function, right? Or injective function. Got it? So again, what is the condition of injective function or 1 function? If f of x is equal to f of y, then after solving this analytically, we should get, that is we must get x is equal to y, right? After solving this. So if this condition will satisfy, then the function will be injective or 1 1, right? So you have 10 seconds to solve or think about this question. After that, we will discuss the solution, right? Okay, let us move to the solution part. So the question says that we have to show that the function f r to r given by fx is equal to x cube is injective, right? So let us move to the solution. The function defined from r to r is given as fx is equal to x cube. So suppose let us take fx is equal to fy, where xy belongs to real. So when we will do fx is equal to fy, so fx is x cube, therefore x cube is equal to y cube. Let us assume this as equation 1. Now we need to show that if x cube is equal to y cube, then x is equal to y. Suppose x not equal to y, right? So their cubes will not be equal, right? If x is not equal to y, then how will their cube, x cube will be equal to y cube? It is simple thing, right? Simple logical thing. So therefore, if like x not equal to y, then x cube not equal to y cube, then like injectivity will not satisfy, right? Simple. However, this will be a contradiction to 1, right? Because we have assumed that x cube is equal to y cube, right? But like uh, by our supposition, we have supposed that x not equal to y, right? But when x will not be equal to y, then how can like x cube will be equal to y cube, right? So x cube will not be equal to y cube, but this will be a contradiction to our statement 1, right? Therefore, this contradict the fact that x cube is equal to y cube. So x cube not equal to y cube coming out to be is contradicting the fact that x cube is equal to y cube, right? So we can say that x will be equal to y. Our assumption was wrong. So we can say that x is equal to y. Got it? Hence the function f is injective or 1 1, right? Got it? The function f is injective or 1 1. Okay. Let us move to the next question. We basically have to find the number of all onto functions from the set 1 to 3 till n to itself, right? Right. So we basically have to find that uh, what can be the number of onto functions from the set 1 to n to itself, right? So what is onto functions? Codomain should be equal to range, right? That means like in the range element, in the codomain element, there will be like all the elements must have pre-image in the domain set, right? In the codomain set, all the in the range set, all the elements must have its pre-image in the domain set, right? For the function to be onto, right? So you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, so let us move to the solution part. So our question says find the number of onto functions from the set 1 to n, 1 to 3 till n to itself, right? So onto functions from the set 1 to 3 till n to itself is simply a permutations of n symbol, right? See, if we have 1 2 3 4 till n, right? And 1 2 3 4 till n. Got it? See, for 1, how many options are there to connect? For 1 there are n options, right? For 1 there are n options. Got it? For 2, since one options has been already been occupied by 1, right? So we are left with n minus 1 options, right? Similarly for 3, 1 and 2 has occupied 2 places, right? So for 3 there are like n minus 2 options. Similarly for 4 there are n minus 3 options. So how many options, how many total options will be there? N options into n minus 1 options, right? Into n minus 2 options, right? Into n minus 3 options till 1. Got it? For the last n there will be one option only, right? One any one of the option only, right? So 1 into 2 into 3 till n is equal to n factorial, right? So onto functions from the set 1 2 3 till n to itself is simply the permutation on n symbol, right? From 1 to n, right? Thus the total number of onto maps from 1 to n to itself is the same as the total number of permutations on n symbol, right? From 1 to n, which is equal to n factorial, right? Simply n factorial. Got it? Okay. Okay, let us move to the next question. See, next question says, let a set A from A is minus 1, 0, 1, 2. Set B is minus 4, minus 2, 0, 2, right? And we from set A to B, we are defined two functions, f and g, from A to B, right? Be a functions defined by fx is basically x square minus x, right? And x belongs to A, and gx is 2 times mod x minus 1 by 2 minus 1, x belongs to A. So R, F and G equal. We basically have to show that R, F and G equal, right? Also we just have to justify our answer that like if F and G are defined as this, and R, F and G are equal, we have to give statement also why it is equal, right? So one hint is there, like you can note that two functions f a to b and g a to b such that fa is equal to ga for all a belongs to A, right? If for all the elements of set A, if fa is equal to ga, right, for all A belongs to A, or if this condition will satisfy, then we can say that the function f and g are equal, right? Right, so are called equal functions. That is, for every A belongs to set A, f of A must be equal to f of g, right? Then only the function will function f and g will be equal, right? Okay, so you have 10 seconds to solve or think about this question. After that we will discuss the solution part, right? Okay, let us move to the solution part. See, we are given a set A from minus 1, 0, 1, 2. B is minus 2, B is minus 4, minus 2, 0, 2. And we are defined two functions f and g from A to B, right? Which is defined by fx is equal to x square minus x, right? X belongs to A, and gx is equal to 2 times 2 times mod of 2 times absolute value of x minus 1 by 2 minus 1. X belongs to A, right? So we basically have to show that we have to show that R, F and G equal functions or not, right? So let us see the solution. It is given that set A is equal to minus 1, 0, 1, 2, and set B is equal to minus 4, minus 2, 0, 2, right? So also it is given that f and g, we are given two functions f and g from A to B are defined by fx is equal to x square minus x, x belongs to A, and gx is equal to 2 times mod x minus 1 by 2 minus 1, right? And x belongs to A. It is observed that, see, what will be f of minus 1? Let us find out f of minus 1. So fx is basically x square minus 1. So let's put the value of minus 1 in x square minus 1. So it will be minus 1 square minus minus 1. So after solving this, we will get 1 plus 1. It is equal to 2, right? So f of minus 1 is equal to 2. So we will check that is g of minus 1 is coming out to be same 2 or not, right? If it is same, then for minus 1 f is equal, right? We will check for all the elements in the set A, right? That for all the elements in set A, either f of x is equal to f of g or not, right? So let us check for g of -1. It will be equal to 2 absolute value of, let us put it as -1, -1 minus 1 by 2, -1. So it will be equal to 2 times 3 by 2 -1, right? So it will be cancelled out, and it like after solving this you will get 3 minus 1 and it is equal to 2. Got it? Clear? Therefore f of -1 is coming out to be g of -1. Now let us check for 0. So f of 0 will be 0 square minus 0, which is equal to 0. f0 will be equal to 0. Let us check for g0. So g0 will be equal to 2 times absolute value of 0 minus 1 by 2 minus 1. So after solving this we will get 2 times 1 by 2. It will cancel out. So 1 minus 1, which is equal to 0. So f of 0 is coming out to be 0 and g of 0 is coming out to be 0, right? Therefore f of 0 is equal to g of 0. Now let us check for, we have already checked for -1 and 0. Let us check for f of 1. So f of 1 will be equal to, fx is equal to x square minus x. So let us check for f of 1. So f of 1 will be equal to 1 square minus 1. So after solving this we will get f1 is equal to 0. Let us check for g1. G1 will be equal to 2 times absolute value of 1 minus 1 by 2 minus 1. Right, which we will get 2 times 1 by 2. It will cancel out. So 1 minus 1 is equal to 0. So f of 1 is 0, g of 1 is 0, right? Right, so f of 1 is equal to g of 1. Now there is one element left, 2. Let us check for f of 2. So f of 2 will be equal to 2 square minus 2, which is equal to 4 minus 2, right, which is equal to 2. Therefore g2 is equal to 2 times absolute value of 2 minus 1 by 2 minus 1, which after solving we will get 2 times 3 by 2 minus 1, right, which after solving we will get 3 minus 1 is equal to 2, right? So f of 2 is equal to 2 and g of 2 is equal to 2. Therefore f of 2 is equal to g of 2, right? So for every element in A, f of A is coming out to be g of A, right? Therefore f of A is equal to g of A for all A belongs to A. Hence the functions f and g are equal, right? All the conditions are satisfied here. So we can say that f and g are equal functions, right? Clear? Let us move to the next question. Next question says that let set A is equal to 1, 2, 3. The number of relations containing 1, 2 and 1, 3 which are reflexive and symmetric but not transitive, right? So we basically have to find number of relations from A to A, right? And and that relation must containing the element 1, 2 and 1, 3, right? And the function should be reflexive, symmetric but not transitive, right? So for this we must know what is reflexive function, what is symmetric function and what is transitive function. So first, what is reflexive function? Reflexive relation. So what is reflexive relation? So reflexive relation is basically for every element in A will belongs to R. AA should belongs to R for AA for all A, right? For all AA should belongs to R for reflexive, right? That is, suppose we have set 1, 2, 3. So 1, 1, 2, 2 and 3, 3 must be there, right? Must be there. Clear? So 1, 1, 2, 2 and 3, 3 must be there for the function to be reflexive. Now for symmetric, what is the condition? For the symmetric, the conditions is if AB belongs to R, if AB is present in the relation R, then this implies BA must be present in the relation R, right? That is, if AB belongs to R, that this implies BA must belongs to R. Suppose 1, 2 and 1, 3 1 3 1 2 and 1 3 must present in the relation. So if 1 2 is present, then 2 1 must always be present, right? And if 1 3 is present, then 3 1 must always be present. Got it? So this 4 element will always be present for the function to be symmetric. Now for transitive relation, for the relation to be symmetric, for the transitive relation, the condition is if AB belongs to R, right? If AB belongs to R and BC belongs to R, right? Then there must be AC belongs to R, right? AC must belongs to R for the function, for the relation to be transitive relation, right? For example, if 1 2 is present, right? See, 1 1 is present, 1 1 is present, and 1 2 is present, right? So 1 1 is present and 1 2 is present, then 1 2 will always be present, which is of course present, right? Clear? And if suppose 1 2 is present and 2 1 is present, right? Then 1 1 must always be present, right? For the function to be transitive. But we basically have to find a function, find a relation in which the relation should be symmetric, reflexive, but not transitive, right? There should not be transitive relation, right? So we have to make sure that condition, right? Okay. So you have 10 seconds to solve or think about this question. After that, we will discuss the solution of this question. Okay, let us move to the solution part. See, we have a set A. Let us first review the question. Let us set A as 1 2 3, then the number of relations containing 1 2 and 1 3 which are reflexive and symmetric but not transitive. So what can we do? Let us see the solution. The given set A is 1 2 3, right? The given set A is 1 2 3. The smallest relation containing 1 2 and 1 3 which is reflexive and symmetric but not transitive is given by. What can be the relation? See, the smallest relation can be 1 1 2 2 3 3 because it is reflexive, so 1 1 2 2 3 3 must be present, right? Now 1 2 and 3 1 should be present, 1 2 and 1 2 and 1 3 should be present, right? So if 1 2 and 1 3 is present, then 2 1 and 2 1 and 3 1 will also be present, right? Now we have to make sure that this relation is not transitive, right? This relation should not be transitive, right? Then only all the conditions will be satisfied. So this is because R is reflexive. Since R is reflexive, as 1 1 2 2 and 3 3 belongs to set R. Relation R is symmetric since 1 2 and 2 1 both both belongs to R, and 1 3 and 3 1 belongs to R. But relation R is not transitive as 3 1 and 1 2 belongs to R, but 3 2 is not belongs to R, right? See, you can say that 3 1 and 1 2 is present, 3 1 and 1 2 is present. So what is the condition of transitivity? That if AB belongs to R and BC belongs to R, then this imply AC must belongs to R. But you can say that, you can see that 3 1 is present, 3 1 is present, 3 1 belongs to R and 1 2 belongs to R. So by the condition of transitivity, right, 3 2 must belongs to R, 3 2 must belongs to R, but it is not belonging to R. You can say that in the relation R, is there any element containing 3 2? No, right? Got it? So 3 2 is not present, so that the relation R is not transitive, right? So this is the smallest relation. Now if we add any two pairs, 3 2 and 2 3 or both, to relation R, then R will be transitive, right? So any relation, like suppose for make it symmetric, we can add 3 2 and 2 3, but when we will add 3 2 and 2 3, the function will become, the relation R will become transitive also. But like we have to find the find that the relation should be reflexive and symmetric but not transitive. So we cannot add 3 2 and 2 3, right? So we cannot think about 2 3 and 3 2. Got it? Hence the total number of desired relations is 1, right? So there will be only one relation from the set A to A which must containing the element 1 2 and 1 3, and the function should be the relation should be reflexive, symmetric, but not transitive, right? So there must be only one relation. Got it? So option A is the right answer. Clear? The correct answer is option A, 1. There must be only one relation. Okay. Okay, let us move to the next question. Next question says, let set A is 1 2 3. The number of equivalence relations containing 1 2 is. We basically have to find the number of equivalence relation. Now, what is equivalence relation? Equivalence relation. So, what are the conditions of equivalence relation? For equivalence relation, function must be reflexive, must be symmetric, right, and must be transitive, right? So for the function to be equivalence relation, for the relation to be equivalence relation, all the three conditions must be satisfied, right? All the three conditions must be satisfied. Got it? Now, since we have set 1 2 3, and the relation must always contain 1 2, right? So for reflexivity, 1 1 must be present, 2 2 must be present, right? 3 3 must be present. Got it? Now for symmetricity, if 1 2 is present, then 2 1 must be present, right? 1 2 is present, then 2 1 must be present. Got it? Clear? 1 2 is present, then 2 1 must be present. So if we take only this relation, then it will be equivalent, right? Because it will be transitive also. Because if 1 2 present, 2 1 present, 1 1 must be present, and it is already present, right? So it must be transitive. So one relation is this one. You can similarly try to find the next relation which will satisfy all the three conditions, that is should be reflexive, one symmetric, and transitive, right? Got it? Clear? So let us take is it reflexive, symmetric, or transitive or not, right? Okay. Now you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, let us move to the solution part. So let A 1 2 3, set A is 1 2 3, then number of equivalence relations containing 1 2 is. Number of equivalence relation containing 1 2 is. So it is given that set A is 1 2 3, right? Set A is 1 2 3. So the smallest equivalence relation containing 1 2 is given by the smallest relation containing 1 2 is given by. So what is your doubt, Lovelin? Can you ask what is your doubt? Okay, see, for the function to be equivalence function, for the relation to be equivalence relation, what are the conditions? The relation should be reflexive, right? Reflexive, symmetric, right? The relation should be symmetric, and transitive, right? Got it? The relation should be reflexive, symmetric, and transitive. So for reflexive, all the three elements must be there, right? 1 1, 2 2, right? And 3 3 must be there, right? Got it? For symmetric, see, we basically have to find the equivalence relation in which 1 2 must be present. So if 1 2 must be present, then 2 1 must always be present for the relation to be symmetric relation, right? Got it? And for transitive relation, if like a b belongs to R, BC belongs to R, this imply AC always belongs to R, right? AC always belongs to R. Got it? So for transitive, this like relation will be satisfied, right? So we'll try to make the relation in such a way that all the three conditions should be satisfied. Got it? So that's why that's what I am explaining. Okay. So suppose we make a relation R1, a smallest relation 1 1, 2 2, 3 3, right? Now 1 2 must be present. So if 1 2 must be present, then 2 1 should always should be present, right? So you can see that the relation 1 1, 2 2, 3 3, 1 2 2 1, right, is reflexive. Reflexive because 1 1 2 2 3 3 is there. Is this symmetric? Yes, it is symmetric. If 1 2 is there, then 2 1 is there, right? Now is it transitive? Yes, it is transitive, right? Because if 1 2 is present, 2 1 is present, then 1 1 must be present, and 1 1 is already present. Got it? Clear? 1 1 is already present, so it should be equivalence relation, right? So one relation is this one. Now we are left with only 4 pairs. Clear? We are left with only 4 pairs, which are 2 3, 3 2, 1 3, and 3 1, right? 2 3, 3 2, 1 3, and 3 1. If we add any one pair, say suppose 2 3, suppose we are adding in this relation, we are adding 2 3, then 2 3 to R1, then for the symmetricity we must add 3 2 also, right? For the symmetricity we must add 3 2 also. Got it? Also for transitivity we are required to add 1 3 and 3 1, right? For transitivity, clear? Suppose we are adding 2 3 and 3 2, clear? So for transitivity we must have to add 1 3 and 3 1, right? Because you can see that three three is there, right? See, 1 2 is there. See, if 1 2 is there, and if we add 2 3, then 2 3 is there, then there must be 1 3, right? There must be 1 3 for the relation become transitive. Clear? So if we are adding say 2 3 and 3 2, then we must have to add 1 3 and 3 1. Got it? Hence the only equivalence relation bigger than R1 is a universal relation. That is, we are adding all the remaining elements in this relation, right? We are adding all the remaining elements in this relation. Got it? Therefore the relation will become equivalence relation. Got it? This shows that the total number of equivalence relation containing 1 2 is 2, right? There must be only 2 relations such that which contain 1 2 and it is equivalence relation, right? So there are 2 relations. Got it? The correct answer is option B, right? So there will be 2 relations. Okay. Okay, let us move to the next question. We are given a non-empty set X. Now consider Px, which is a set of all subsets of X, right? Now define the relation R in Px. Define the relation R in Px as follows. For subsets A, B in Px, A related to B if and only if A is subset of B, right? A related to B if and only if A is subset of B. So is R an equivalence relation on Px? So we have to basically justify our answer, right? So we are given a non-empty set X and we have to consider Px, which is the set of all the subset of X, right? we have to consider the set Px, which is a set of all the subset of X. Got it? Right? So you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, let us move to the solution part. Now, given the question says, given a non-empty set X, we basically have to consider a Px, which is a set of all the subset of X, right? Now, define the relation R in Px as follows. For subsets A, B in Px, A related to B if and only if A is subset of B. A is subset of B. Is R an equivalence relation on Px? We basically have to justify our answer also. So let us move to the solution part. Now, since every set is subset of itself, right? We know that every set is subset of itself. So if A related to A, for all A belongs to Px. So symmetricity is clear, right? All the set is subset of itself, right? Got it? Therefore, R is reflexive. Reflexivity is clear. Got it? Because all the set is subset of itself. Now let if A related to B, this imply A is subset of B, right? So this cannot be implied to B subset of A. See, if A is subset of B, this cannot, then there is no, we cannot say that B is subset of A, right? This does not imply. So for instance, suppose we have elements in set A as 1, 2 and element in set B as 1, 2, 3. Then it cannot be implied that B is related to A, right? Because B is not subset of A. Here A is subset of B, A is subset of B, but B is not subset of A, right? Therefore, R is not symmetric. Clear? R is not symmetric. Further, if A related to B and B related to C, then A must be related to B and B must be related to C, right? A must be subset of B and B must be subset of C. Got it? If A related to B, that means A is subset of B, and B related to C, that means B is subset of C, right? So for transitivity, A must be subset of C, right? So A must be subset of C. This implies A related to C, right? Therefore, R is transitive here. Got it? Got it? Suppose A is subset of B, right? A is subset of B, right? And B is subset of C. That means A will be subset of C. Got it? A is subset of C. Clear? Suppose A is 1, 2. B is suppose 1, 2, 3. 1, 2, 3. Right? And C is suppose 1, 2, 3, 4. So here A is subset of B, right? A is subset of B and B is subset of C, right? So when A is subset of B and B is subset of C, so you can see here that A will be subset of C, right? A will be subset of C. So the condition for transitivity is satisfied. Got it? So if A is subset of B and B is subset of C, then A will always be subset of C, right? Whatever relation you can take. Clear? Therefore, R is transitive, right? Hence, R is not equivalence relation, right? See, it is reflexive, it is transitive, but it is not symmetric, right? So R is not equivalence relation because for equivalence relation, the relation should be reflexive, symmetric, and transitive. All the three should be satisfied. But here, only reflexivity and transitivity is satisfied, but not symmetricity. Got it? Hence, the function relation R is not equivalence relation, right? Got it? Okay. Now, if R1 and let us see next question. If R1 and R2 are equivalence relation in set A, you have to show that R1 intersection R2 is also an equivalence relation, right? R1 intersection R2 is also an equivalence relation. So you have 10 seconds to solve or think about this question. After that, we will discuss, right? Clear? We know that intersection, suppose we have set A as 1, 2, 3, right? And set B as suppose 3, 4, 5, right? So what is A intersection B? We know that A intersection B is 3, right? Clear? So in such a way that if R1 and R2 are equivalence relation in set A, so we basically have to show that R1 intersection R2, that is intersecting portions in R1 and R2 is also equivalence relation, right? Okay, so you have 10 seconds to solve or think about this question. After that we will discuss the solution part. Okay, let us move to the solution part. The question says if R1 and R2 are equivalence relations in set A, and we have to show that R1 intersection R2 is also an equivalence relation. So let us see the solution. Since R1 and R2 are equivalence relations, so A belongs to R1 and A belongs to R2 for all A belongs to A, right? Clear? This implies that A will belongs to R1 intersection R2 always, showing that R1 intersection R2 is reflexive relation, right? R1 intersection R2 is reflexive relation. Got it? Further, if A AB belongs to AB belongs to R1 intersection R2, right? This implies AB belongs to R1. If AB is belonging to R1 intersection R2, then this implies AB is belonging to R1 also. And AB belongs to R2, this implies BA belongs to R1 and BA belongs to R2, right? This implies BA belongs to R1 intersection R2. Got it? Hence R1 intersection R2 is symmetric always, right? So it is reflexive always, it is symmetric always. Let us check for transitivity. Similarly, AB belongs to R1 intersection R2 and BC belongs to R2 intersection R2. For symmetricity, what condition must we satisfy? If AB belongs to R1 intersection R2 and BC belongs to R1 intersection R2, this implies AC must belongs to R1 and AC must belongs to R2. Right? This implies AC belongs to R1 intersection R2. Let us check. This shows that R1 intersection R2 is transitive. Got it? Clear? If you will take any element AB which is belonging to R1 intersection R2 and BC which is belong to R1 intersection R2, right? Then AC will always belongs to AC will belongs to R1 and AC will belongs to R2, right? This implies AC will belongs to R1 intersection R2. Got it? This shows that the R1 intersection R2 is transitive. Got it? Clear? Thus we can say that R1 intersection R2 is an equivalence relation, right? R1 intersection R2 is an equivalence relation. Okay. Okay. Thank you so much.